Oh. A coil of just going to measure .1 ohms. No. No, for some reason. Rather sound. Adjustment. 6 volts. 9. So why first time? No, because the meters we're using measure RMS values, which is a straight line equivalent of the sine wave. Yep. So, but that's good that you're thinking like that, but that's not exactly what it is. So these meters measure a DC equivalent of the AC waveform. That's called the root mean square value, RMS. You heard of that before? No. More of that in electrical principles in year 3. All right. There's another reason why you're not getting so much current on AC as you get on DC. Any other ideas? Sorry? What about it, Tom? Yeah. Exactly. That's exactly what it is. Okay? When you connect, we're going to come back to these results later, okay? After I've shown you, or we talked about why that happens, and then we can find out the difference between resistance, the opposition to current in a DC circuit, and what's called, someone mentioned it earlier, impedance, the opposition to current in an AC circuit. And that value is a complex value. It's got a magnitude and a direction. Right, so we're back to our complex numbers that we were doing in maths a couple of weeks ago. Okay, to a certain extent. And this theory is around one of the practicals you're going to do for your assignment that I'm going to give you this week, but you're going to start on it next week, so don't worry. Okay? Got some practical work to do before you can start on that. Alright? So, electromagnetic induction. 2 laws govern electromagnetic induction. Faraday's law. Okay? Faraday's law says that a voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field, and that the magnitude of this voltage is proportional to the rate of change of flux. So that's a complicated, worded explanation of Faraday's law. Lenz's law says the direction of an induced EMF, according to, so this EMF induced because of Faraday's law, the direction of that EMF is such that it will always oppose the change that's making it happen. So there's a change going on that's causing this voltage to be induced, and that voltage will be in a direction that actually resists the change, holds it back, if you like. Okay. So, if we pass a DC current through a coiled up conductor, like we were doing over here, just turn it off if it's too hot, okay, we produce lines of magnetic flux. And what we end up with is that the flux will produce an overall field with a north and a south pole. The rules for magnets are that they form, these lines of flux form complete circles. They have a direction which is north to south outside the magnetic material. So these are going from north to south, they go the opposite direction inside. Okay. The other main rule of magnetic flux is they don't cross. So they'll oppose crossing, which is why when you bring two north poles together you get the repellent action that you get with a magnet. Okay. The strength of this field that we get in this electromagnet can be increased by putting more turns on the coil, increasing the current, and adding a ferrous core, an iron core, so we support the field better, because that will exist much stronger in something, in a piece of iron or other magnetic material than it will in air. Okay, but what we've got there is a magnet that we can turn off and on effectively, and we can change the poles, because if we reverse the direction of current, we'll reverse the north and south poles. Yeah. So you see these big magnets on a crane that pick cars up with, electromagnet. Turn it off and on, DC current. You turn it on, top of the car, pick it up, turn it off, it falls off. Okay. A little bit more complex than that, but we don't need to go too deeply into magnetism at this stage. So that's the kind of thing that would be used as a coil on a DC relay if you're used to them at work. Yeah? You'll have this pole here pulling the contacts in, make them open and close. Alright? If this electromagnetic induction, Michael Faraday discovered that if a magnet was moved in and out of a coil, it induced an electromagnetic force, EMF, or a voltage across the coil. And therefore, in a closed circuit, you'd produce a current. Yeah, you should bear in mind that the EMF will also be produced if we keep the magnet stationary and move the coil. It's relative movement between the two that causes that action. Okay? If we take this diagram and we say we're going to move that north pole and move it into that coil, we'll produce a current in one direction. As we pull back out again the opposite way, the relative motion's reversed, you'll get current in the opposite direction. If we turn the magnet round, those two directions will be reversed, because we're entering a south pole in and taking a south pole out. So the direction of that current induced is chosen by the poles of the magnet and the direction of movement. And again, we can get more EMF if we add more turns, increase the field strength of the magnet, or we move the magnet faster. The most important thing that you should remember is no movement, no induction. As soon as that magnet or coil stops moving, the induction stops happening. Yeah. Are you all quite happy with that? Yeah? So that's in DC. If we put this same inductor, which effectively becomes a coil of wire, becomes an inductor once we put it into an AC circuit. Okay. AC by definition is constantly changing direction, and we're talking about a sine wave AC at this stage. It's going to go positive in one half cycle, negative in the other, and it's going to be climbing until it hits a peak and then falling to a negative peak and back up to zero again. So the field consequently is building up as it rises to this peak, falling away as it goes up to here, and then expanding again in the opposite direction to the negative peak and then falling away. So the flux is changing constantly in an AC circuit. If you imagine that flux collapsing and building up, when it's doing that, that's cutting across the coils in the wire, and therefore that's inducing an EMF in the coil itself. So you're applying a voltage, you're applying a current, but there's also another voltage being induced. And if we're applying a voltage in that direction to force current back the other way, that's Lenz's law. So effectively, there's more resistance to the flow than you would. It's the current flow the most. Sine wave. Let's draw it a bit bigger. Where is the induced EMF? There. Remember, we're going back a little bit on math. The rate of change of voltage is highest when the voltage is crossing zero. When is there going to be no induced EMF? There and there. Yeah. What this causes is the current and voltage to be out of phase with each other. More about that a bit later, but if this is our voltage on a scale like so over time, current will end up because of this. Yeah. Right. Again, more about that soon. I don't want to go too deep. I'll explain why we get less current on DC than we get on AC, and what we're leading up to, part of the experiment you do for practical, find what the inductance of that coil is in, and we can do that using these values that we've measured. Alright? So by Lenz's law, will induce a current that opposes the change that has caused the induction. This means the applied current is in the direction shown and the induced current is opposite to it. The induced current will never get as big as the applied current. It's not possible, but it's going to restrict it for a certain length of time, catch up, and restrict in the opposite direction. Because remember, the applied current is constantly changing because of this sine wave. Yeah? So, when the applied voltage is positive or negative peak, the rate of change equals 0, so no current. So if this blue sine wave here is the voltage, when it hits the peak, there's no current because the voltage is not changing, the current's not changing. As we go across 0, we get a peak in current. So we end up with, if we could have an inductor that didn't have any resistance, not possible in the real world because a coil of wire has got some resistance. we'd end up with a voltage, and we always draw the in-phase component, the one that starts at 0 degrees, as the horizontal left to right. So that line is up. We end up with a current that is 90 degrees behind, downwards. So there's a 90-degree angle between voltage and current. Yeah. Remember, we're talking about angles here, but we're also talking about time. So the current one peaks after the voltage one, lagging behind it. A lot of students make the mistake of thinking if it's lagging behind, it must be over this way. No, that's leading, because it's peaking sooner. Yeah? Okay? So for a pure inductance, current lags the voltage by 90 degrees. Yep? All happy with that? So, the inductive reactance of a coil. It's called its inductive reactance. It's got L being the symbol we use for an inductance, right, and X being the symbol we use for reactance. So XL, it's measured in ohms. So we've got resistance, we know already it's measured in ohms. Now we've got XL measured in ohms. Because the induced EMF and current will be greater if the applied voltage changed faster, the magnitude of the inductive reactance is dependent upon the frequency of the applied voltage. Think about it. I said if we move the magnet faster, the field cut faster, we get more voltage. So if we increase the AC frequency from 50 Hertz upwards, that suggests we make the magnetism change quicker, or we're going to get more induced voltage. This X is a quantity that will vary with frequency. Alright? And we can calculate it using the formula XL is equal to 2 pi times F, the frequency in Hertz, times L, the inductance in Henries. So, if we increase the frequency, the inductive reactance will increase and less current will flow. If we reduce the frequency, the XL will get lower and we'll have more current flow for a given voltage. Okay? So, unlike resistance, reactance is frequency dependent. Resistance doesn't change when we change frequency, but reactance does. Alright? Anyone, any questions so far? Now, a real coil can never be a pure inductor because of some resistance. Sometimes negligible, sometimes could be quite big if there's lots of turns. Okay, and remember what that was? That was 6 point some odd 7 ohms or so, was it? We got it right. So what we can do is represent a real coil as an inductor, our inductance XL, in series with our resistance R. Yeah? The resistance of the inductor does not change with frequency, but the reactance does. This leads to a different term being used to describe the opposition to current flow in an AC circuit. That new term is called impedance. So it's resistance in AC, impedance in resistance in DC, impedance in AC, where the impedance is a symbol Z and also measured in ohms. So these two together have got a combined impedance that is Z. Yeah? And it's equal to R plus XL. I'm going to put that on there. J. What does the J describe? Imaginary number, but it brings in that 90-degree angle that we've been talking about. Yeah? Of XL being, and the current being at phase. It's just so that we can represent, if we're talking about this coil, we can represent the resistance as a series resistor. So that whole thing is that sitting inside the box. So inside the box you've got an inductor representing the inductance of it in henries, and in series with a resistor representing its resistance. What you can't do is go inside that coil and put a meter on just the resistor or just the inductor. That's what you can't do. You can talk about the voltage that would be across there and across there, but you can't measure them. Yep? There's a way of representing a real coil. Right? Because it's always going to have some resistance. In some cases that might be so negligible that you can ignore it. Nevertheless, there's always going to be a little. Yep. Note for DC current, frequency F is equal to 0. That means XL will also be 0, because you're multiplying 2 pi times L by 0, outcome is 0. So once we get to 0 frequency DC, the fact that there's an inductor there makes no difference. It's just treated like a resistor on its own. Okay. So what we need then now to talk about is the impedance triangle. We always have 0 degrees as the left to right from the axis. So resistance is represented along the x-axis, R ohms. XL is a positive 90 degrees. We've got XLJ, remember, a positive J term is horizontal, vertically upwards. 90 degrees out of phase with the resistance, so that's XL in ohms. If we then complete that parallelogram, like so, and take the diagonal, that is the impedance Z in ohms. And we end up with an angle between that. So that phasor is Z ohms angle theta. It's a complex value. We've got a vertical component of XL and a horizontal component of R. Okay? Yeah? The impedance of the phasor is the sum of R and XL. By Pythagoras we could find the magnitude of Z by doing the square root of R squared plus XL squared on that triangle. And if we wanted to, we could find the angle using one of the trig ratios. Yeah. Right. So how does frequency affect this? Well, if we have no frequency, i.e. DC, then they're both in line with each other. Okay, and we have an impedance that's equal to the resistance. At low frequency, we've got a certain amount of XL, a certain amount of R that doesn't change. We end up with an impedance of a certain length. If we increase frequency above, so let's say, I don't know, double it or something, resistance still changes the same, but the XL line gets longer. Therefore, the length of the Z line is longer, and the angle has steepened by increasing frequency. Consequently, reduced frequency, less angle, shorter Z line. So, for an inductor, the higher the frequency, the less current will flow, because Z, the overall impedance, is getting bigger. Yeah, and they end up further and further out of phase with each other. It's getting bigger. Right. All these different quantities can be complex numbers that we've been using in maths in either form. Reactance, look at our frog. Let's use our measured values. So, DC, what volts did we apply? 6 volts. What current did we measure? .89 amps. Therefore, R is equal to V over I 6 of 0.8 equals 89, sorry. In the light of what we've applied in the other values, how many significant figures would you have that for? What? I'll go with that. Yeah. Certainly not loads and loads, but you must bear in mind with practical readings that you can't really quote any more significant figures than those that you measured. Yeah. In a way, really, we should go with 2. We'll stick with 6.74. So the length of this line, 6.74 ohms. Yeah. Now, AC current was measured, front page, 0.7. Therefore, Z is equal to VAC over IAC. Perhaps we ought to qualify this with DC and DC as well there. Yeah? So that is 6.5 divided by 0.7 equals 9.3 ohms. So the length of this line, 9.3 ohms. So now, using Pythagoras Theorem, we can find XL, can't we? That rearranges to XL is equal to the square root of Z squared minus R squared. Can't see that rearrangement, say so. That is square root of 9.3 squared minus 6.7. Which is, gents, no, it's not minus something. Six point. So this is 6.4. Yep. Now, using XL is equal to 2 pi FL. F in this case is equal to 50 Hertz. That rearranges to L is equal to XL over 2 pi F. 6.4 over 2 times pi times 50. .02. Any more figures? Yeah, 0.02 henries equals 20 millihenries. So, using DC current to determine the resistance, because we know inductance doesn't do anything with DC current, and using AC to determine the impedance, and then doing a bit of calculation gives us the inductance of this coil. And you're going to do that in your practical work. Alright? With a variable inductor at various positions. So, yeah. And actually, we're on a different coil of wire, different inductor. Chris has measured, I've measured the inductance using this method, and Chris has used an induction measuring instrument costing about £2,000, and the results concur. So, all right. Assignment 2 for science. So assignment 1 is O'Mal's mechanical one. Assignment 2 is this electrical one. So issue today, 22nd of March. Submission date, 3rd of May. Yep. So you got a good while to do it, but you've got to get some practical done before you can do it anyway, really. Okay. You're going to be applying direct current and alternating current theory to solve engineering problems, and more specifically, practical investigation to determine unknown component values using DC and AC theory. Yeah, it's worth 20% of the overall mark for the module. So each assignment is worth 20, and each exam is worth 30. Yeah. So, assignment task, more detail further down, but carry out a practical lab using AC and DC theory to determine the values of 3 unknown capacitors and the value of a variable inductor. Write a clear lab report for each experiment that analyses and discusses the results in the light of known theory. Yeah? So you've got to upload your report before 23:59 on Thursday the 3rd of May 2018. Various restrictions and other bits and pieces that are standard for all the assignments. Okay. Level 4 grade and matrices in the task. So you're required to use your theoretical knowledge together with the use of practical lab equipment to determine the values of some unknown components, capacitors and a variable inductor. Important that you keep extensive lab notes and calculations so that you can write up your report after the lab is completed. Yeah. Yeah, go on, it's up to you. You will be given 3 capacitors where factory markings have been removed and replaced with the labels A, B and C. Alright? Devise a practical lab experiment to determine the value of these capacitors using their discharge cycle. So you're going to time the discharge cycle using the theory that we talked about the capacitor charge and discharge. You're going to use that to find out what the value of a capacitance is in microfarads or farads. So you're going to be given 3 capacitors. You're going to use the discharge cycle to take some readings and use that to work out what the value of the capacitor is. I'm going to give you some guidance, yes. Alright, I'm going to do that. But that's the idea, is that you're devising something yourself. Alright? When you've done all that, you've got to write up a lab report for that particular experiment. The purpose of the lab: carefully referenced research, outlined the electrical theory behind the lab work undertaken. So what's the electrical theory related to the capacitor discharge cycle? You'd need to do that. Yep. Equipment used, okay. How the equipment was set up. Circuit diagram. I ought to put that in big letters. Not a picture of the equipment, a circuit diagram. Because the idea of a good lab report is that somebody else reading your work could repeat the experiment, maybe with different equipment to you. So it's a circuit diagram that they need, and then you can say in your procedure, set up circuit as shown in circuit diagram, figure, whatever. But a picture is not a circuit diagram. You can take a picture of the equipment by all means, but that isn't the circuit diagram. No, the circuit diagram should be in the main report. Yeah, you can have that. Photos and diagrams don't cost you any words. So why not have them in there where they're doing the job, which is in the main text? I don't really see too much need for appendix here. There might be one place, and I'll point that out to you in a minute. Alright? Outline of the methods used, so someone could repeat it. I don't want I connected wire from point B to point C and then from point C to D. Circuit was set up as shown in the diagram. Voltage was set to. Readings were taken every, and then you notice I'm saying were. I'm not saying I, we. Third person, please. Anonymizer. All right. Clear summary of the practical results. That suggests a table. Okay. If you're measuring voltage to 3 digits, every reading that you record should be 3 digits in that column. So you eventually read exactly 2 volts. You should put 2.00. Yep. Not 1.37, 1.98 and then 2.00. Alright? all to the same resolution. Clearly laid out calculations that you've used to determine the value of the components from the results. Okay, so you need to show calculations. In this case, there's not very many, so you'll show all of them in one place. Okay, and then discussion of the validity of your findings in the light of component tolerances. Once you've determined your values, okay, I will give you the nominal values of those three capacitors and what their tolerances are. You can then compare the results you got with what the can says, 20 microfarads plus or minus 10% or whatever it is. You can see whether your results lie in that tolerance band, and that'll help you analyze those results and whether you think they're valid or not. Yeah? You should remember that one of the key purposes of the lab report is that it would allow someone reading it to repeat your experiment work with success. Yeah? So they should be able to follow what you did, do it again, and get similar results. All right? Investigation 2. So there's two parts to it. Second investigation, you'll provide with an inductor that's got that's an variable inductor, carry out experimental measurements. So we got two of them. Okay. You may work on one, you may work on the other. All right. You're probably going to work in pairs, although we got an odd number. But we can sort that out. Someone else can help the spare person anyway. It doesn't matter. All right. These inductors have got a movable and removable laminated core, iron core, that will vary its inductance. I'll just get one out. Right. Well, as we got time, get this done now. Okay. Practical 1. You're going to have a variable DC supply. Yep. You're going to plug into that, and I'll tell you why it's important. I'm going to plug into that in a minute. All right. You're going to come up and use your unknown capacity. Yep. And then you're going to be given that has mega ohm. Yep. What you're going to do then, switch on and charge this up, this capacitor, up to a voltage. 20 volts. Yeah, it's going to be... Alright? Now, this power supply here is one of these. Yeah? Remember what you're going to do, you're going to charge it up to a given voltage, chosen by you, and then you want to discharge it. You're going to discharge it through the meter. So the capacitor is charged. Switch, and we just switch this off. There's an internal resistance to that, and that'll discharge through the power supply. So what we need to do to discharge, take one plug out. When you do that, you're going to get a current flow from the capacitor through the meter back through there. That's the discharge current. Okay, you're going to time the discharge to a suitable level such that you know you can calculate. So remember, time constant, that's what you want to remember and think about how you're going to do it. Time constant is equal to 1 times C times R. We want to find, or you want to find, that value. Yeah? You know that value, 1 mega ohm, because that's the resistance of the meter. 1. I'll take the 1 away. That's actually, so that's equal to C times R, yeah? Time constant, C times R. You also know, do you not, that VC is equal to, I'm not going to give you all this, VC is equal to E to the power of minus T over CR. You want to find what CR is, that's the time constant, because then you can rearrange that formula, find C. So how long are you going to, how long are you going to discharge it for, or what voltage are you going to discharge it down to? Be able to determine what C times R is. Look back at the previous 3 on the capacitor charge cycle. See if you can work out what. What you're interested in, time constant, and therefore once you've got the value, remember we talked about this being long on this experiment, you can act level, if you remember, we talked about it, calculations of what the voltage level would be after one are in the class. Read it. Look. Yeah. You didn't map out it because it's move this core as soon as you regard an amp and you do that, that might go to 1.3 amps, move it, settle down. So for each core position you're going to use an AC voltage, again through an ammeter and with a voltmeter connected. Here's your variable inductor. Okay. For each core position using Ohm's law. Yeah. Calculate XL. Calculate L. One's using and calculate L using XL is equal to 2 pi. That example we done today, except you're going to do it time for each. Type of paper set out on paper, all the need, write it in carefully, make sure they're kept until you put it in your report. That's an line. Two capacitors. Got plenty of